This webinar talks about the contribution of AI to answering questions about behavior change interventions. My name is Pol Mac Aonghusa, and we're part of the computer science team contributing to the Behavior Change project. Well, I guess we could start by just reflecting a little bit on why we're here. Behavior change and behavior science is not alone. We see this across many scientific and indeed many disciplines. We're snowed with information. We see many more reports emerging. Keeping up is a constant challenge, and not just keeping up, but also extracting useful information and applying that information to solve real world problems is proving harder and harder. And so it's a natural question to ask, how can we apply modern technology to help us address some of these challenges? And particularly if in the context of the Behavior Change project, if we can address better reporting of interventions and also find ways to help organize and then crucially use or synthesize the organized information in useful ways to help produce faster, better, more robust inferences about the likely outcomes of behavior change interventions. And so in a nutshell, they're the kind of questions we ask ourselves each day. Are we helping progress these as part of the computer science work that we're doing in the way we apply artificial intelligence techniques to the behavior change project? Now, I guess before going much further, I'd just like to pause and maybe motivate, and apologies to all the purists out there. I'm not going to go into this in huge detail, so there won't be enormous amounts of technical detail here, but I do want to cover off a number of key concepts just to motivate some of the following content and subsequent webinars. And the first area to stop and really is to ask, what is AI, at least in the context of the Human Behavior Change project? I mean, a pretty general, high-level description of artificial intelligence is a way of constructing complex systems that solve problems that you'd normally associate with human intelligence. And that covers a vast array of things. The literature in artificial intelligence is absolutely enormous. We really only use two core pieces of the vast amount of material that is covered by that large part of the Venn diagram. The first of these is natural language processing. And this is particularly crucial for us for the Human Behavior Change project, because the objects that we deal with are documents. They're typically written in PDF format. They're typically reporting the results of behavior change intervention trials. And so being able to teach the computer to read a document successfully is key. And natural language processing is the area that covers this type of activity. The other is machine learning. And so machine learning here is teaching a computer, but we have to be very careful. It's a mechanical kind of teaching. What we're really doing is showing examples to a computer and encouraging the computer through technology to learn patterns that occur in the documents. And so a lot of the work that we had to do early in the Behavior Change project, for example, was to read through lots of behavior change reports and annotate them, point to places in the document where we saw examples of interventions, where we saw useful information that we thought the computer should learn to read. And so machine learning in this case is just training a computer to learn patterns from large sets of example data. The core result then at the end of this is that we hope to build a system that learns how to go from examples that we've prepared to then being able to read documents that we haven't prepared. And so that our hope then is that the computer will be able to interpret unseen examples. In artificial intelligence, this is called generalization. And so you're moving from specific examples that you've shown the computer to general cases where the documents are no longer part of that training set or example set that you've shown to the computer. And so what do we do with all of this technology, natural language processing and machine learning? Well, really two core things, and these will be touched on by my colleagues later on in the webinar. The first is information extraction, and you can simply think of information extraction as reading through the document and picking out the interesting bits. So dates, times, ages of people, examples of the interventions that have been applied during the trials, and putting them into some kind of format that we can then use for future processing. And what do we mean by future processing? Well, the example that we're going to talk about today is prediction. So how can we use all of the results of information extraction to create some kind of prediction about likely outcomes of behavior change interventions? And we will also talk about that later in the webinar. The next term that I just wanted to touch on briefly was ontology. So this is an interesting term because the history of ontology goes back a long way, pre-computer terms. And that's kind of useful in this case because the ontology is a bridge for us. It's a bridge between the language or the vocabulary of the behavior change community and the language of computer science. Because it turns out that ontologies are also pretty useful for computers. They tend to structure information in ways that computers find easy to process. At its core, you can think of an ontology as a model of the world. It picks out all of the main things that you're likely to encounter in a behavior change intervention report, or at least things that are interesting for us in terms of future prediction or consumption of the information. And then it helps us create all of the connections between those things. So it tells us about the relationship between things. And so you might think of a behavior change report containing, for example, ages of participants. Is it a randomized control trial or not? Is it, for example, how many arms are in the randomized control trial? And so all of these pieces of information have a home somewhere in the ontology structure. And so you'd think that after processing a document, what we are really doing is then creating a clone or a mirror of the key information that's in the document, but we're organizing it consistently across all documents so that it's represented in the way that the ontology is structured. So if you're familiar, for example, with databases, you might have heard words like schema. And so you can think of an ontology in our case as a schema. It's the abstract way that we would represent any behavior change document. And so in our case, all documents that we process, we organize the extracted information exactly according to the ontology structure, which is pretty useful then for subsequent processing, because what we can then do is pass a consistent set of information into our machine learning algorithms. And we can begin to ask questions. And so here's an example of how we might do a prediction. What we can allow the user to do is to give us information about, say, a population, a particular intervention type that they're interested in, and then a type of outcome that they're also interested in. Because we've organized everything in a consistent way according to the ontology structure, the computer finds it pretty easy then to walk through that structure and to pull relevant information together that it thinks might be useful in answering that question. Most of the algorithms that we have then built up allow us to say, well, what evidence can we find that would allow us to predict an outcome for that combination of information, for that population, for that intervention and that outcome? And in this example that I've shown here, the predicted outcome value is about 9%. And we also give a kind of a time period that we would associate with the outcome. And so you see that you're training the computer to walk through the corpus of documents and to pull out the kind of information that you would have had to extract yourself and maybe perform some kind of further analysis to try and normalize all of that information, try and put it into a consistent framework so that it could be compared, and then trying to pull out what you thought was a reasonable outcome value. All of that is happening now inside the machine learning algorithms that have been created as part of the project. And so I've touched on a number of key terms that I think are important for the rest of the webinar. And now I'll hand you over to my colleagues. I believe Martin is going to follow now to talk a little bit about the information extraction process. Thank you.
Hi, I'm Martin, and I'm going to talk to you about the two components, kind of the two steps of our system, which are information extraction and prediction. I'm going to first start with information extraction, and I'm going to explain to you what this is, why we need this step, and also kind of our method to achieve this information extraction. So first of all, at its simplest, information extraction can be described as finding and labeling the key pieces of information in a study report. So you see an example here that I try to highlight. So you would have an entire, like a paper in PDF format that would be, like about smoking cessation and some kind of intervention on some population. And I kind of zoomed in onto the abstract, and in the abstract, you would kind of read the abstract in its entirety, and you would stop onto what you think is key pieces of information, like these two numbers here that we highlighted with kind of the blue rectangles, which would be like mean age and number of cigarettes smoked, and that would be the information that you're trying to extract. So obviously, the question that is instantly raised here is what makes the information key or not in this case. And so that's kind of the question that our behavior change scientists try to answer in this part of the project of HBCP. And so the focus was really about what describes the behavior change interventions most accurately. And so in this example, we thought that knowing the mean age of the participants of the interventions in this smoking cessation study, for example, was very important, right? It goes the same way for the number of cigarettes that they smoke, right? Which is in this case about 20 per day. So this information, right? This information is what we called key in this case, and that's what we're trying to extract. This is based on what we call the BCIO, which is the behavior change intervention ontology. And ontology in this case is basically like a fancy word to say that it's a way to structure knowledge, right? So, but basically the behavioral scientists listed for us all the important information to retrieve, to extract, and that's what we are doing in this step. All right. So now I think you might wonder, like, why do we do information extraction at all, right? So we have the data, we have the text, so we could design some kind of computer system that would read the entire text and do some kind of very smart AI thing on the text itself, right? So, but that's not how we do it, and we have this extra step of information extraction. So I'm going to give you some reasons for why we need that step. So I could come up with two answers to that question. One, which is kind of obvious and very intuitive and very easy to understand, but which I don't think it's very actually that useful, as far as computer science goes. But the second one is a bit more difficult to understand, but it's actually the more important, the most critical ones for our work. So if you had an information extraction system, one way in which you would use it is, through interactions with actual users. Let's say, people that are trying to look for informations, such as, like a policymaker, maybe that would be interested for some reason into finding all of the smoking cessation studies that involve people of about, 47 years old. Instead of themselves, reading through all the papers to try to see, the age of the participants and all that, they would just use kind of a simple user interface, and they would search for all the papers that have a mean age of 47 as extracted by the information extraction system. So that would be like a very direct use of information extraction system. So you can kind of see it as a very domain-specific kind of Google search type of application. But the second one is actually what we are interested in this presentation. So and it's actually much more important for information extraction as a whole. Like I think most information extraction systems are used in this way. And so they're actually used by other computer systems, right? By computer systems that are actually trying to do things that are a bit more complicated and smarter than just, highlighting a bunch of text, like a bunch of words in a text, which sounds kind of simple, right? So these other computer systems would try to do something a bit smart with this information. And so in this case, they would try to work obviously on behavior change knowledge, right? So that's why we would use these behavior change papers that go through the information extraction process. And so the very concrete example for us in HBCP, in the computer science team of HBCP, is the prediction system that we want to build. And the prediction system would obviously have to ingest a lot of knowledge on what are the important characteristics and descriptors of the interventions are and how they affect, for example, the outcomes of it. So our team of behavioral scientists, experts, annotated a lot of these papers on specifically smoking cessation, actually more than 500. And when I say annotate, I mean that they read all the papers one by one, painstakingly. They read it very attentively, and then they, every time they think some information, is part of what we consider like very critical information for the intervention, they would highlight it, right? So they would do it on a computer, but you can imagine that you would have done it maybe like on a piece of paper. You would have highlighted with these flashy markers or highlighters. You would do exactly the same, but it would be kind of the computer version of it where you highlight the text with your mouse, right? So they went through that process, and then it was our job, the computer scientist team, to basically teach from these data, right, from these annotations, teach the computer to try to do exactly the same, right, to go from these PDFs, these papers, to the version of them with these annotations, these kind of highlightings of all the important information, right? So this process where you try to teach a computer, like, to try to make them learn how to do something that has previously been done by human beings correctly, right? That's called supervised machine learning. And that's what we use here to achieve this information extraction system. But now the prediction system, the goal of it is to answer the question, what proportion of a given population would stop smoking if they went through a given intervention? That's the question that we want to answer. You can already see that's kind of akin to predict the future, right? Because we obviously want to do it without actually running the intervention, right? Without actually having to go through that process. And so this should be something that only the machine does. And so we actually go through roughly like the same high-level process as the information extraction from before, right? Which is called still supervised machine learning. And so for the prediction system, to try to learn how to answer these kind of questions accurately, we need to basically extract like a lot of questions and a lot of their answers from the papers, right? Because the papers, you can view them as kind of these questions plus the answers, because we actually did here, we actually ran the interventions there, and we have the outcomes, which are the answers. And so the prediction system will try to learn from that. And so just to conclude this part and to tell you that there is nothing really truly magical or that comes out of nowhere in this process, which is sometimes what people see in machine learning or artificial intelligence. The prediction system is really only as good as the evidence in the papers, the evidence that we managed to extract using the information extraction system. And so that's what we can qualify as an artificially intelligent system in the end.
The Human Behavior Change Project pulls together a really diverse and interesting group of people from behavior scientists, computer scientists, and information science. And our goal really is to help create a system where we want to address what we call our big question. And really it's to look across the vast and continuously growing corpus of literature in behavior science, and try and help people understand that when it comes to interventions, we want to be able to figure out what works, compared with what, for what behaviors, how well, how long, with whom, in what setting, and why. Why is this important? Well, you're not alone in behavior science. Every field is growing. We are generating so much more information, and it's becoming increasingly harder to keep up, but also to compare across the corpus. And so The hope is that by combining all of the different skills and diverse backgrounds, we can create an artificial intelligence-based system that will help us read through the documents, organize them in interesting and useful ways, and then help us to draw some conclusions that will help us progress the big question. In order to do this, we've got lots of different components. We go from lots of different behavior change reports, intervention reports. We call the evaluation reports here. We use structures like ontologies. Feature extraction is something that I will talk to you about today. We organize things into a knowledge base, or a BCI database, as it's called on this chart. And then we have lots of machine learning and AI algorithms to help us process this and to create useful outputs. And of course, finally, we do need something that a human can use. And so there is a user interface, not just for humans, but also for computers. I'm going to talk a little bit about two key topics on this report. The first is feature extraction. And you can think about feature extraction as, how do we extract useful content from a report? Think of a document containing lots of sentences, lots of words, lots of tables. In fact, lots of things that we possibly don't need to know about in order to do useful work, but we still got to read through it. And so, can the computer do this faster? Can it do it more reliably? And can it extract features that perhaps we don't even really recognize are in the documents? And so that's the task of feature extraction, which Martin will talk about. The reason we do all of this is to then be able to produce useful outcomes, to synthesize the information, to answer user queries. And the particular area that we focus on is prediction. So given a combination of inputs, things about population, setting, and so on, can we produce a likely outcome about what intervention we think is most likely to work, given the scenario that we've been given as part of the user query. Now, this is a lot of work. We've got a lot of different moving pieces here in technology terms. We've got a lot of people contributing. And of course, some things work well and some things work not so well.
To summarize the information extraction work, we developed a machine learning system which can extract a larger number of entities from RCTs in PDF format. And compared to the inter-annotator agreement, our system achieves reasonable results for entities which do not frequently appear in tables. So at the moment, effectively extract entities from tables is still a big challenge for our system. So our system can be used in several downstream applications, for instance, information retrieval, evidence summarization, and behavior change prediction. Later, my colleague Martin will talk about how we leverage information extraction system for prediction. Finally, I would like to say a few words about future directions for information extraction. First, as I said before, at the moment, our system is still struggling to effectively extract entities from tables. So moving forward, how to combine the two modalities. One is a table, the other is the surrounding context together to do the inference between these two modalities, and then improve the performance of the information extraction system is an interesting research direction. Another direction is few-shot learning. So as I said before, annotation is a very time-consuming task for HBCP. So how to leverage the explanation of the entity is a very interesting direction moving forward. And then in this way, we don't need to like annotate a lot of entities, but the explanation of the entity itself actually contain rich semantic information about the entity, how to design a system to learn the description of the task, and then using that to extract information effectively is an interesting research direction. And finally, is about transfer learning and domain adaptation. So at the moment, we are working on two domains, smoking cessation and physical activity. And we noticed that there's some overlap between these two domains, which means a system learned the knowledge from the smoking cessation can transfer to physical activity. So if we want to so scale up the system to working on like multiple domains under behavior change science, and then we have to design an efficient approach which can leverage transfer learning and domain adaptation to work in practice. So yeah, that's basically about the work in information extraction. Thanks for watching, and then I will hand over to my colleague Martin to talk about prediction.
So first of all, so I'm going to talk to you a bit about what it is to predict the outcomes of behavior change interventions. And so for smoking cessation, for example, that would be the percentage of people in the study that quit smoking after a given period. For physical activity, it would be something else. It would be the minutes per week, for example, of moderate to vigorous physical activity. And you can see that it can be very diverse, right? The outcomes themselves, but they're mostly always some kind of number. And so the system that we are going to build, the prediction system, is going to logically be a regression system that try to solve a regression problem because we're trying to predict a number. So you could maybe like at first glance you would think that each study in the data set maybe could be kind of an instance to the machine learning problem, right? But that's the way in which we work here is that we consider like each arm, which means the study groups, right? So you can imagine inside of a study there would be most often at least two study groups, kind of one where you try the actual intervention, right, which would be the intervention group, and at least a second one, which would be more like a control group where you would find, you would do something a bit less advanced, or maybe you would not do anything at all, or something like that, right? So you have several study groups inside the same study, and so that's how we're going to create our instances. Each of them will have its own outcome because these are different populations and different arms, and so they have different outcomes, and so all of each arm will be a different instance. And so during training, you can imagine that we are going to describe accurately all the parameters of each arm, which is kind of the input of the problem, and then the output will be the outcome. Let's say in smoking cessation, it will be a simple percentage like that, right? So, and this is going to be the training set, and so we are going to train our system on that. And then when comes the test phase, or let's say the runtime, when we are presented with completely new behavior change scenarios, unseen arms with unseen parameters, things that we haven't seen before in training, obviously, then the task will be to predict the outcome, and that's kind of the regression problem. So this regression problem, right, is we found it very challenging for several reasons. And so the first one is that it's intrinsically a difficult problem, right? So even for human experts, let's say you were to gray out all the outcomes inside the study reports, they would have a very hard time, trying to fill out the blank, right, and to fill out the grayed out part to guess the outcomes. So, and it's especially true if you gave them only like a brief description of the intervention and the population. You were saying like, oh, these people are X years old, they have, they're mostly balanced in terms of gender, blah, 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 blah. And then you say, oh, we did this and that as part of the interventions to them. How many do you think will stop smoking, right? It's a very, very difficult question to answer. It's kind of akin to predict the future, right? You never know, what's going to happen. So, from the get-go, it was always going to be a difficult problem, I think. The second part is that just from the machine learning standpoint, we have a lot of entities that we consider very important to describe the studies and to describe the interventions. So we have 82, like Yufeng said. And so that's as many features as we're going to use in the regression system. But unfortunately, we don't have that many training data. Actually, we have less than 1,000 arms. So you can imagine that's less than 1,000 instances. So when you see, 82 features and 1,000 instances, it's not really something that you want to see in machine learning, right? To be perfectly honest, right? So that's also like a second difficulty. And then finally, something that's kind of goes deeper is that the prediction system is trying to work with a simplification of the study report, which is, like all the entities that we try to extract from it, and that the behavioral scientists also annotated from it, right? So they kind of boiled down the study reports to an ontology and to a bunch of annotations, a bunch of entities that are kind of just a simplification of it, right? So we hope that's as accurate a simplification as we can, but it's still a simplification. And then to add to that, on top of that, and I think even most importantly, right, the study report is itself a simplification, obviously, of the real life scenario, right? What happens in the real world. So obviously, you don't really know, if people will have tried their best, performing the interventions, how many, the researchers writing the report might have left out some kind of details that are actually important. The numbers might be, misreported or things like that. Like there are like a million of things that could happen that could make the study report stray a bit far from the real life scenario, right? And so that's when you combine all of this, right, all of these kind of simplifications compound, and so it ends up with kind of a prediction system that has a very inaccurate view of what happened in the real life, right? And so that's kind of also what makes this problem very difficult, because how can you expect prediction system to be able to predict the future if the data that it starts from are not really completely accurate, right? That's kind of the difficulty. Thank you very much.